Hello and welcome back to Educator.com and welcome back to Physical Chemistry. So today we're going to start our discussion of spontaneity and equilibrium. So we are coming to the end of thermodynamics. We're going to close out that circle. And here is where everything absolutely starts to come together and we start to seriously apply these things to chemical reactions. So let's jump right on in. Okay, so the following terms mean the same thing as irreversible. We'll often refer to an irreversible transformation as a real transformation, natural transformation, spontaneous transformation. Let me go ahead and use the blue ink here. This is going to be the word that we use the most often. So when we talk about reactions, you remember from general chemistry, we talk about spontaneity, a spontaneous reaction. Has nothing to do with speed. It's just a thermodynamic quality, and we'll talk about it a little bit more. So irreversible, real, natural, or spontaneous. Okay, so here's what we want to do. We ask ourselves, what differentiates a reversible or an ideal transformation? So ideal transformations are ways of dealing with things that we've been dealing with them, but they're not real. They're ideal in the sense that they provide an ultimate way of looking at things and they help us put together some sort of a mathematical structure for it, but it's not a real transformation. The real world doesn't work that way, but it gives us a standard, a reference. So what differentiates a reversible transformation from an irreversible transformation, a real one? And we consider the relation between the heat that flows and the entropy change that accompanies that heat flow in a given process. Okay. During a reversible process, a system deviates only infinitesimally from equilibrium. We've talked about that a lot, especially when we talked about energy. The system does undergo a transformation, but it is essentially at equilibrium during the whole step, because you're only deviating slightly from where you are, so essentially you're at equilibrium. Therefore, the condition of reversibility is the condition of equilibrium. So the defining equation for equilibrium is this one right here. TdS equals dq reversible. And all I've done, this is just a rearrangement of the definition of entropy. We had ds is equal to dq reversible over t. All I've done is multiply both sides by t so that I can write it in this form without any fractions, if you will. So the defining condition for a system to be at equilibrium is TdS equals dq reversible. Okay. Basically, that means that when a system is at equilibrium, the differential change in entropy that system experiences times its temperature is going to equal the differential change in heat. I'm sorry, not the differential change in heat, the little bit of heat that flows in along a reversible path. So this is the defining equation for equilibrium. Okay, now the condition for irreversibility, for a real transformation, is actually the Clausius inequality. The Clausius inequality, the ds is not equal to dq over t, or dq reversible over t. ds is going to be greater than dq over t. Notice we've gotten rid of the reversible part, and now we have this greater than operator. So, upon rearranging, we get the defining equation for irreversibility and spontaneity. This is what's important right here, this. So once I've multiplied by that, I get that. This is the defining equation for a spontaneous process. This is the equation that we're going to play with and manipulate, okay? This is it. It starts right here. A spontaneous process, a natural process, a real process, one that happens on its own without any external help. This is the condition for it. T times ds is going to be greater than the dq. Okay, we can combine these two equations by writing this. Basically, all I've done is greater than or equal to, where we take the equality to sign to mean a reversible value of the dq. So if the heat exchange happens to be done reversibly, that's all this is. It just includes all possibilities. Our concern is going to be this one, greater than. It's always going to be like that because every real process is this right here. So this is the important equation. What does this say? It says the transfer of heat during a spontaneous process, this right here, the transfer of heat, is less than the entropy change for the process times the temperature at which the process takes place. Once again, for a particular process, a spontaneous process, the heat that's transferred during that process is going to be less than the entropy change for that process times the temperature at which the process takes place. That's the defining equation for spontaneity. That's the one we're going to manipulate. Okay. Now let's go ahead and get started. So we have this T ds is greater than dq. Oh, sorry, greater than or equal to. I'll try to remember that. Now let's go ahead and recall our the first law of thermodynamics, our energy. We know that du equals dq minus dw. Let's go ahead and rearrange that. So we end up in solving for dq, we get dq equals du plus dw. And then we can go ahead and put this expression for dq into here. So we end up with the following. We end up with T ds is greater than or equal to du plus dw. Now let's go ahead and rearrange this. I'm going to bring both of these over to the left-hand side, and I'm going to leave 0 out on the right-hand side. So I have minus du minus dw plus T ds is greater than or equal to 0. This right here, this is our defining equation. All we've done is we've taken that defining condition, we've included the first law of thermodynamics, so we've brought in the heat and the work and energy, and now we've expressed it this way. This is the defining equation for a spontaneous process. The negative of the differential change in energy minus the work that is done in that process plus the temperature times the differential change in entropy is always going to be greater than or equal to 0. This defines a spontaneous process. If you have a system and this is satisfied, the process is spontaneous. That's it. If you know a process is spontaneous, this will always hold. Okay. Now, so far, we've only looked at pressure volume work. So far, we've only looked at let me actually write that out. We've only looked at PV work. Okay. This dW right here, it includes all work, not just pressure volume work. Maybe there's some electrical work done. Maybe there's some other mechanical work done. Who knows? This is a combination of all the work that's done, not just expansion work. So this dW includes all work. Now, we're bringing this up because we want to make this discussion as general as possible. For our purposes, and I'll get to that in a minute, we're not really going to be concerned with other work. We're only going to be concerned with pressure volume work. And sometimes when we start putting constraints on this equation, we're not even going to be concerned with pressure volume work, because if the volume change is 0 under constant volume, the pressure volume work is 0. So all of these terms start dropping out. But we want to give the most general conditions for a spontaneous process, and then we're going to tighten it up by placing some constraints on it, okay? So don't worry if things start to look a little too complicated. They'll get very, very simple in a minute. So far we've only looked at pressure volume work. This dW includes all work. So we have this dW is going to equal the pressure volume work, which is the external pressure times the change in volume, plus, and I'll write dW sub other, whatever other work that is. We don't really care all that much. When we put this expression in for here, we get the following. We get minus dW minus P external dV minus dW other plus TdS is greater than or equal to 0. Okay? This is the equation we want to concern ourselves with. This is the one we start with. These two equations actually are going to be the same. Sometimes we're going to talk about work cumulatively. Sometimes we're going to separate work out into pressure volume work and all the other work. but these equations are absolutely equivalent. So sometimes we'll start with this one to start our derivation process for new equations. Sometimes we'll start with this one. They are the same. Okay, so we've now expressed the condition of spontaneity in terms of changes of the properties of the system. We have the energy, we have volume, we have pressure, we have the work done, we have temperature, and we have entropy. All of these things are now, we've expressed it in terms of all of the properties of the system. This is the condition of spontaneity. This is the condition of spontaneity. Okay. So now we do what we normally do. We take this condition, we take this as the basis equation, and we start putting constraints on it, because in the laboratory, it isn't just a free-for-all. In the laboratory, they're normally, you're going to have conditions of constant temperature and pressure. That's going to be the majority of it. But sometimes we're going to constrain the volume. Sometimes we're going to constrain the pressure or the temperature. So now we take this, place those constraints on it the same way we did for energy, the same way we did for entropy. Remember, we did constant temperature, constant volume, constant temperature, constant pressure. Now we're going to do the same thing. We're going to take this equation, constrain it to derive a new set of equations under laboratory conditions, the things that we normally run across. Okay. So the first one we're going to talk about is transformations in an isolated system. Okay. Just for the sake of being complete. So transformations in an isolated system. Transformations in an isolated system. Excuse me. Now, when a system is isolated, there is no exchange of energy. You know what? I'm going to go back to blue, I think. I really, really like the blue. So there's going to be no exchange of energy. So du is equal to 0. Well, there's no work done in an isolated system. So d equals 0. And there's no heat exchange. So dq equals 0. So if we have minus du minus dw plus t ds is greater than or equal to 0. I used this particular one with just the generic cumulative work. Well, that's 0. That's 0. What I end up with is t ds is greater than or equal to 0. And then, of course, I get ds is greater than or equal to 0. In an isolated system, the entropy of that system will always increase. By isolated means it's completely separated from everything. It has no interaction at all with its surroundings. No exchange of energy, no exchange of matter, no exchange of anything. The entropy of an isolated system will always increase. Okay. A little bit of a caveat with respect to this one. It isn't just the entropy of the system that's going to increase. The truth is, it's actually going to be the change in entropy of the universe that's actually has to be greater than or equal to 0. Now, the entropy of the universe, the change in entropy of the universe, is going to be the change in entropy of the system plus the change in entropy of the surroundings. In this particular case, we're isolated, so it's not really going to include the surroundings. But let me just go ahead and bring this up here, and I will talk about it later. It is actually possible for a system itself to have a decrease in entropy, provided that in the surroundings, the entropy increase more than compensates for the decrease, so that the total entropy change of the universe is always greater than 0. This is universally true. This is true for an isolated system. So again, we are talking about an isolated system. Then the ds of the system is always going to be greater than or equal to 0. But in general, what we're really going to be concerned with, I mean, how often do we deal with isolated systems? We don't. I mean, the fact of the matter is we don't. There's always going to be some surrounding involved. This is just for mathematical completion. We just wanted to use this equation. In an isolated system, this is what happens. So let me just go ahead and mention this, but we will get back to it and discuss it in more detail. Okay. So now let's start getting into the real important aspects, because we're not going to be dealing with isolated systems. Let's go ahead and talk about transformations at constant temperature. So now, if we hold the temperature constant, isothermal process, here's what happens. So, excuse me. So transformations at constant temperature Now let's go ahead and start with our equation. Minus du minus dw plus T ds is greater than or equal to 0. Okay, so we're going to have to find a way to manipulate this. So here's what we're going to do. When temperature is constant, excuse me, when temperature is constant, I can rewrite T ds equal to d of Ts. In other words, I can put the Ts together. The differential operator actually operates on both, but since T is constant, this T actually comes out, which is why we write it TdS. So all I've done is rewrite it in its more original form. So the temperature times the entropy, when I differentiate it, when I take the differential of it, because temperature is constant, it comes out. So I'm going to, instead of writing TdS, I'm going to write dTs. So we have minus du plus T ds. Okay, I'm going to go ahead and move this dw over to the other side. I mean, again, you don't really have to. It's just different ways of looking at the same equation. So the derivation itself, you can leave the dw on the left. You can put it on the right. We're actually going to do both. When I do the summary of conditions in the next lesson, I'm actually going to bring everything to the left, and I'm going to leave a 0 on the right. So greater than or equal to dw. So this is just moving things around. Well, this is going to be minus du plus a dTs greater than or equal to dw. I'm going to go ahead and factor out the differential operator. You can do that. Minus du minus Ts greater than or equal to dw. We end up getting this thing, minus the differential of this thing, greater than or equal to dw. Again, energy, temperature, entropy, and work. Now, this combination right here, this U minus Ts, it shows up so much, we actually give it a special name. So, combination of U minus Ts. Remember what we did with enthalpy? We said enthalpy is equal to U plus PV. So enthalpy is a composite function. It's a composite of the energy of the system plus the pressure of the system times the volume of the system, and we called it the enthalpy. This U minus Ts, it's just another composite. So now we define this thing called A, the Helmholtz energy. So A happens to equal U minus Ts. It's a composite function, okay? It's a combination of the energy, the temperature, and the entropy. Not altogether different than this. So, A is the Helmholtz energy of the system. Helmholtz energy of the system. If I know the energy of the system, and if I know the temperature and the entropy of the system, if I multiply the temperature by the entropy and subtract it from the energy of the system, I get the Helmholtz energy of the system. That's all it is. It's just I've just put something together. It's an accounting device. I don't want to deal with U and T and S, so I'll just say U minus Ts is this thing called Helmholtz energy. So that's what we get. Okay. A is a state function. The Helmholtz energy is a state function. Well, of course it's a state function because it's a combination of state functions. Energy, entropy, temperature is a state function. So we have minus d of this U minus Ts greater than or equal to dw. Let's go ahead and we said that A is equal to the U minus Ts, so we can write minus d of A greater than or equal to dw. There you go. Or, upon integration, if I integrate this, I end up with minus delta A is greater than or equal to W. Again, it's not delta W, it's W. under conditions of constant temperature, the work in a given process, for a spontaneous isothermal process, the work done during that process is going to be less than or equal to the decrease in the Helmholtz energy. That's what this is saying. Okay, so let's write this down. So what does this say? What does this say? It says, in a spontaneous isothermal process, the work produced in the surroundings, or if I just want to refer to the work in that process, regardless of the particular point of view that I'm taking, the work produced in the surroundings is less than or equal to, it's going to be less than, the decrease in the Helmholtz energy. Just follow the math. Not a problem. Now, notice that, let me go back to blue here. Notice that dW, we said, is going to be equal to this pressure volume work, so PdV plus other kinds of work. Okay, so it includes all the work. Now, in general, we're not going to be concerned with other work. We're only going to be concerned with pressure volume work. So, in general, we will concern ourselves with PV work only. So, we have minus delta A greater than or equal to the W. We have minus delta U minus TS greater than or equal to W. I can distribute the delta operator, so I get minus delta U plus T delta S greater than or equal to W. It's starting to look for a little bit familiar. Or, if I want, I can write it as, if I go ahead and switch this sign and move some negatives around, if I make the delta U positive, delta U minus T delta S is less than or equal to, negative W. There we go. It's another way of looking at this. So, now, when Helmholtz energy is taught, so let's write this out. When Helmholtz energy is normally taught, it is taught as constant temperature and constant volume. It is taught as T constant, which is what we've done, and V constant. So normally, chances are in your book, you're going to see this introduced as, if I hold temperature and volume constant, what do I get? That's usually how they introduce this notion of Helmholtz energy. Now, if V is constant, that means that this right here, this portion of the work, is 0. Okay? Because if V is constant, if there's no, then dV is 0, so that there is no pressure volume work. And the only work you have is work other. Well, we just said that in general, we're not going to concern ourselves with other work. So if we're going to drop this, so we have dW equals P external dV plus dW other. Well, if we're going to forget about the other work, and if we hold volume constant, then this is going to be 0, then this is going to be 0. And here's what you end up getting. You end up with minus dA greater than or equal to dW. That's our basic condition. Well, if dW is 0, we get minus dA is greater than or equal to 0, or if you want, dA is less than or equal to 0. Or the integrated version, delta A less than or equal to 0. So this is normally what you're going to see in your book. Under conditions of constant temperature and volume, the change in Helmholtz energy for a spontaneous process is going to be less than 0. This should start to look familiar. You're accustomed to the delta G being less than 0 for a spontaneous process. Well, delta G happens under conditions of constant temperature and pressure, which we're actually going to be talking about in the next lesson. But there is this other energy in the system, this energy which is the energy minus Ts, which is the Helmholtz energy. And if I hold the temperature and the volume constant, then this, for a spontaneous process, it's the change in Helmholtz energy, the delta A, that is going to be less than or equal to 0. So now let's go ahead and just finish up with by writing a couple of different versions of this. So delta A less than or equal to 0. And once again, in your book, you're going to be introduced to Helmholtz energy as constant temperature and volume. But in general, the volume does not have to be held constant. It's the temperature that has to be held constant. You can go ahead and leave the volume there, and then this work term is not 0. If we ignore all the other work, we're still going to be concerned with the pressure volume work that's done. So this is the general version of this. Okay? This is the specialized version that holds T and V constant. V does not have to be constant here, so don't think that it has to be. Okay, so this is that. So let's go ahead and write delta U minus Ts less than or equal to 0. This is going to be delta U minus T delta S less than or equal to 0. And of course we have our delta A is equal to delta U minus T delta S. There you go. This is the basic relationship that exists. This is similar to the relationship that you learned in general chemistry, which we're going to learn again, which is, just as a little bit of a preview, delta G equals delta H minus T delta S. Remember that one? Yeah, this is the Helmholtz version of it. So under conditions of constant temperature and volume, this is what you get. This is what you get. All of these things are equivalent. This is the general equation right here. That's the general version of the equation. This is the one for temperature and volume, for constant temperature and volume, constant temperature and volume. So please remember, you don't have to hold volume constant. You have to hold temperature constant. If you hold volume constant also, you end up with a 0 on the right-hand side. If you don't, then some pressure volume work is going to be done, and there's going to be a work term. And again, we're not going to be concerned with other work. If there was other work, electrical, mechanical, that would also be part of the work term. Hope that makes sense. Thank you so much for joining us here at Educator.com. We'll see you next time for a discussion of Gibbs free energy. Bye-bye.